All right, folks, it's Bass Action back in action here. We are finally wrapping up this really big chapter on exponentials and logarithms, and these final pages of notes will just be all of our applications. Those applications are going to give us a chance to review all of our solving skills, which is a great way to end the chapter. Now, this page of notes is going to cover our problems that talk about uninhibited growth and decay. And these problems will give you an actual formula that will just follow this pattern. And in that pattern, all you're really expected to do is interpret it and solve for various parts of the formula. So let's first understand really quickly what the different parts mean. On the left-hand side, the n of t, this is going to be the ending amount of whatever you are trying to get, okay? So maybe you want to know how many cells are there after a particular period of time, or something like that. The n itself, this is going to be our beginning amount. So if it asks how many were there when the experiment started, that's what you're looking for. Our k is going to be our rate. It will always be listed as a decimal. And our t is going to be time. Now, time on these problems are always going to be relative to whatever that particular problem is talking about. So let's just look at an example here. As you can see, it says a colony of bacteria are growing according to the law of uninhibited growth. That phrase is telling us that it's following this pattern, and it's going to be modeled by the function, and they will give it to you. They're going to be modeled by the function. It says n of t 100 e to the 0.045 t, okay? It says that n is measured in grams and our t is measured in days. So now we know what our time is going to be measured in, and that's important when we go to label our answer as well as the n. So when it says what is the initial amount of our bacteria, that's our beginning amount. So really we're just looking for that 100, that coefficient right here. So our answer, we don't even have to do any computation. Our answer is 100 grams. And I know it's going to be grams because that's what it said the problem was in. When it says what is the growth rate of the bacteria, again, just thinking about the parts of our formula, the growth rate is going to be that decimal that's in the exponent. So our growth rate is this 0.045, but of course we wouldn't typically leave it like that. We would write it as a percent. So we're going to take our decimal and we're going to move it 2 places. So we're actually going to say our growth rate is 4.5%. That is a much more meaningful percent for us. Now, it also wants us to say, what is the population after 5 days? So when it's asking for the population after 5 days, it's talking about evaluating this function at 5. So that means we're just putting 5 in for t. So we're going to say 100 e, and we're going to say 0.045 to the 5th power times 5. And at this point, this is really just a calculator problem for us. So we're going to type this into our calculator, and we're going to get, when we type this into our calculator, we are going to get approximately 125.2 grams. Now, it didn't say what it wanted us to round it to, so I just took it to tenths. Obviously, the textbook will tell you what it wants you to round it to. If it's talking about like insects or something like that, we would want to have that be a whole number because it wouldn't make sense to have a partial insect. So that would be our answer. Now remember, just a little review here. As we enter this in, this E, you're going to find this E on your calculator using your second or shift button on that natural log. If you're having trouble typing this into your calculator, please make a note, put a little star on this page, dog ear it, so that we can talk in class how to do this calculator work. Now, the next question is going to ask us how long. So when it asks us how long, that immediately implies that we're looking for time. So as we plug things in, we're expecting for that to be our remaining variable. So if we're looking for how long will it take the population to reach 140 grams, that means that the ending amount's going to be 140. Then it's going to equal the 100.045t. And just as we expected, t was our remaining variable. So we're going to start by dividing both sides by this 140, or this 100 I meant to say. So if I divide both sides by 100, those are going to cancel. And on this side, what I can see, even without a calculator, the zeros will cancel. The 14 and the 10 are going to reduce to a 7 over a 5. That's going to make this a little bit easier to write in our next step. So we're going to have this 7/5, and we're going to have e to the 0.045t. And this problem really is just like all the things that we've been doing earlier in the chapter. It's just the numbers look a little bit grosser to us. So we have an exponential. We need to solve for that. We're going to switch to our logarithm. So we're going to have a log base e that at this point you're probably pretty good with just saying, oh, well, that's the natural log then of 7/5. So that log base e becomes natural log of 0.045t. Now we're going to finish this last little bit up, and we're going to say that our time is going to be the natural log of 7/5 divided by 0.045. So we can type that into our calculators, and we'll have the natural log of 7/5, and that's going to be divided by 0.045, and that's going to get us approximately 7.5. And remember, t was measured in days. So again, just a good application of how to do our solving. Our last question here says, what is the doubling time? So again, we're looking for time, okay? And it wants to know the doubling time, meaning how long is it going to take for this population to double? Now, this is an important question. They ask us this question pretty frequently, this type of question. So, and we'll start to find a pattern here in a little bit. But if we started off with an initial of 100 grams, then if it's going to double, then our ending amount is going to be 200. And then, of course, we still have the 100, e to the 0.045t. Just like before, we can divide both sides by 100. That, of course, is going to clean this up very, very quickly. So I can just write this as a 2, e to the 0.045t. Just like before, we're going to switch to our logarithm. Of course, log base e is going to become natural log. So it's going to be natural log of 2 equals 0.045t. So our time is going to be the natural log of 2 divided by 0.045. And we could type that into our calculator. And when we type that into our calculator, we're going to get approximately 15.4 days. Okay, so this is a really important thing of just being able to interpret those various formulas that we're given for our uninhibited growth. The next thing that we do want to take a look at here is some payment periods. We're on our next videos and pages of notes, we're going to look at compounding interest. So understanding this vocabulary is crucial. If interest is compounded annually, it's only compounded once per year. So we're going to have a once here. If it's compounded semi-annually, that's going to be twice per year. Quarterly is 4 times per year. Monthly, there's 12 months in a year. It's going to be 12 times per year. Daily is a little bit odd sometimes because even though we have leap years in the financial world, daily is always considered 365 times per year. And continuously, this is a very, very important one. If you see that language anywhere in the problem that anything is compounded continuously, you are automatically going to assume that it is E, Okay, so E is our natural log. It's going to become the base of that, and we will be thinking E on all of those problems. All right, so on the next few pages, we're going to jump into applications of the financial formulas and how to solve for those.